That's a great point. Saad, can you,
Yeah, it's on.
oh, it's recording already. Okay, great. Cool. Okay, yeah. So welcome to day 3, Geometric Satake. So today we're going to start sort of going into the actual proof. So hopefully that's exciting. As far as the schedule for today, we're sort of going to start with some general motivation for why we should think this is something that's true. I feel like Saad's already given us like pretty substantive sprinkled motivation. So maybe that won't be completely new, but we'll sort of get a sense of why this is a statement that we should somewhat think is true before we get to proof. And then we're going to spend a long time talking about the affine Grassmannian, which is sort of an object that's important in its own right, but is sort of the protagonist of this. So yeah, so first maybe just some references for the proof. So the main references, already talked about this, but Mirkovich and Volonen's paper, where they originally proved it, it's actually really good. Sometimes original papers are a little bit messy to read, but I think it's still probably the best reference. There's also a paper by Bowman and Risch that sort of goes through Mirkovich and Volonen's argument in a little bit more detail. I think it's good for some parts, which could be a little bit confusing. And then there's also a great paper by Xinwen Zhu. It's from 2016. I don't remember what it's called, but it sort of has a more modern approach, talks more about things in terms of G bundles and relationships to Lagrange and stuff like that. So we're more going to sort of follow these two, but I think this paper, has a lot of great stuff. And as Saad talked about, there's this textbook that's in progress by Pramod Achar that you can reach out to us if you want to sort of look at it, because it hasn't been published yet. And if you have it, you shouldn't make it publicly available, but I should cite it because I've definitely been using it for part of the proof. Okay, great. So second and final, not super exciting thing, sort of notation / conventions. So we're going to let O be power series in P, let K, big K, be Laurent series. Little k can just be sort of algebraically closed. Characteristic 0. So you might never actually see little k, but it's always going to be secretly there. Is like whenever we have any types of sheaves, they're like sheaves of little k vector spaces. So I'm probably not going to write k every time, but it's always there. G, an affine algebraic group scheme, or just algebraic group, I guess. That's redundant. Over C, be a Borel, and T, a maximal torus. And then we have sort of these guys, GK and GO. So I think honestly the best way to think about them, especially for the purpose of the mini course, is just to think we're just going to let G be a matrix group, and GK and GO are just going to be matrices with coefficients in that ring. But if you're someone that wants to think of these things as functors, then they are also just the k points and the o points of G sort of as a functor of points, which I think we should recall because it's actually going to be important, is just maps, in this case from spec K to G, and in this case from spec O to G. And we're going to call this guy sort of the formal disk. So you want to think of it as sort of the disk around the point, but like an infinitely small disk. And this guy is sort of the punctured disk. So maybe those are sort of already familiar to people, but if not, just sort of keep that intuition throughout. Also, if you're the type of person who wants to make sure that everything is a functor, you can sort of just define GK of some ring R to be G of R Laurent series, and you can do a similar thing, which I'm sure you guys can figure out from for GO. But that perspective is not going to be super important for us. Great. Okay. So now let's move on to sort of motivation. So let's sort of start by thinking about sort of co-roots for a second. So our torus, just C star to the N. I know Saad wrote GM. That's probably even better, but I'm going to write C star. So all of these co-roots are just algebraic maps from C star to T. And in particular, they're all just going to be maps of the form sort of T goes to T to the I1 down to T to the IN, right? They're all just sort of a power in each component for these IJs, R and Z. So if we want to, we can sort of think of this already as sort of an element of the torus with points in K. So sort of look at just these functions sort of in the coordinates, and we already sort of have an element of TK. So in particular, we have sort of this map from co-weights to TK, which also lands inside GK. And then it sort of turns out that we can actually just write, it turns out that GK is just a disjoint union over dominant co-weights of GO. And this map, we're just sort of going to denote, if we have some lambda, we're going to denote that guy is just T lambda. T lambda times GO. And in particular, this is just another way of saying the fact that GO double cosets in GK are in correspondence with dominant co-weights. But thanks to Saad's lectures, we already know that dominant co-weights are sort of in correspondence with something else, which has been important so far, which is representations of G dual. So this is already the first place where we sort of see what we might consider like a shadow of geometric Satake. It's kind of arguably crazy even that we already sort of have like a bijection between something like representation of G dual and these sort of double cosets, but the limitation is that this is really only a bijection at the level of sets. So we have 3 sets here, and we identified all 3 of them, but it's all purely sort of sets. So our goal,
Alberto?
yeah.
Sorry, I think I missed what O was purely out of my own negligence.
No, that's actually a great point, which is, for me, that's always really tough on Zoom too, to just like, because you write something at the top and I tend to always want to look back to it. So if anyone ever misses something, like I'll just scroll up and like, yeah, you should just tell me and I'll happily scroll up. So O was power series in C. It was, I mean, it's right here.
Okay.
Cool. And K is Laurent series.
Thanks.
Yeah. And just to reiterate something else, we should think of sort of spec O as a formal disk and spec K as a punctured formal disk. But yeah, so we have this sort of our first version, maybe we might say, of geometric Satake. So what's our goal here? Our goal is to upgrade this to a categorical statement. And not only do we want to upgrade this to a categorical statement, but we want to upgrade this to a categorical statement sort of with a symmetric monoidal structure. So for those that you guys don't know, symmetric monoidal structure basically just means a tensor product. So on the left, we have, on the right, we have the tensor product that we all know and love. Also, yeah, I see in the notes, the comments, Tom made a really good point. Like, this is a highly canonical bijection. Like, it's not just like, we found 2 sets that happen to have the same size. But it's still just a sort of a set bijection right now. So we want to upgrade this to a categorical statement. We also want it to have a symmetric monoidal structure. So on the right, we know we can have a tensor product of representations. On the left, it's a little bit more confusing what we're going to have. A lot of you can probably guess we're going to have some kind of a convolution based on the fact that that was important in Saad's talks, but maybe it wouldn't be obvious just from the get-go. And lastly, we sort of want simple objects to be labeled by dominant co-weights. So that's sort of the name of the game. So if we're trying to do this, we might think, well, representations of a reductive group are semi-simple, so we can just express everything. Okay, actually, I noticed I already made a huge mistake. Maybe not huge, but this should have said irreps. So this is just irreps of G check. But that comes back to what we're saying. So our first try, we might say, well, rep G check is a semi-simple category. So we can make all the representation just by taking direct sums. So why don't we just sort of take functions on both sides over, say, the non-negative integers. So our first try might be to say we take functions on non-negative integers in double cosets, and that's going to be in correspondence with rep G check. And you'd be right at a level of like an abelian sort of like an abelian category with no symmetric monoidal structure. But this is not really going to have an easy way to upgrade to a symmetric monoidal structure. So this is sort of not going to work. And a lot of times in math, sort of when we want to move sort of up from a statement of functions to a sort of higher categorical statement or to a more categorical statement, what we do is we try replacing functions with sheaves. It's sort of a big heuristic. You can sort of think of sheaves as maybe like packets of functions, but without sort of going too far into trying to justify it. Maybe our second try would be to think, okay, well, I'm going to take sheaves on GO mod GK mod GO and see if that's the same as rep G check. So I'm being sort of purposefully vague because this statement is not going to be super meaningful as is. So we have sheaves on double cosets, but you know, double cosets just as a set are not going to give you very exciting sheaves. So now we sort of have the issue of the fact that these double cosets seem to have lost a lot of the geometry about how these GO sits inside GK. So the idea is going to be to replace sort of naive, by naive I just mean like normal quotients with equivariances.
Hey, Alberto.
Yep.
Quick question. So in this try one that you wrote up here, is that, do the set of double cosets form some kind of group or something? Like this looks like a
so
grouping,
right
like
there, I literally just meant like functions, and like you can like add the functions, and on the right you can like take direct sum. So they are like abelian categories, but that's like about it. Yeah, it doesn't have a convolution structure. That's exactly why like try one was not a very successful try.
Okay.
That's not something that's going to upgrade to like something with a symmetric monoidal structure. But anyway, yeah, so we were just saying we want to try to replace these quotients with equivariances. So just as a sort of like justification / strategy note on doing this, so if we have sort of an algebraic group G of variety X, then G equivariant sheaves and G acts on X freely, then G equivariant sheaves on X are literally the same thing as sheaves on X mod G. So now what if the action of G is not free? Well, then for this statement to remain true, we'd have to sort of delve into the world of stacks, which is not something that we're going to do in this mini course, but sort of X mod G, we could define as a stack quotient precisely. This would be true. But we're not going to go there. This is more of just sort of a heuristic as to why we want to switch quotients with equivariances. And that's like a smart thing to do. And these equivariances, if the action is not free, are actually going to do a better job sort of remembering the geometry. In particular, we have that GO acts on GK freely, say on the right. I mean, also on the left, but for now, let's just say on the right. But not on GK mod GO. So the first quotient that you take, it doesn't really matter. Yeah, the first time you take a quotient, it doesn't matter if you sort of take equivariant sheaves or if you take a quotient. The second time, it does. So in particular, instead of taking these, or the best way to say is the way we're gonna interpret these sort of sheaves on double cosets is we're gonna interpret them like this. So try 3 is gonna be, we're gonna take GO equivariant sheaves on GK mod GO, And we're going to say that this is equivalent to rep G. And now we're basically there, except for the fact that I've been purposefully vague about what I mean by sheaves. So in particular, maybe unsurprisingly, the sheaves that we're going to work with are going to be perverse sheaves. That's sort of the category of sheaves that we're going to be taking. So now we can state geometric Satake. So perverse GO equivariant sheaves on GK mod GO are equivalent to rep G check as, I'm going to write as tensor categories, but it would be slightly more correct to write as symmetric monoidal categories. So maybe the last looming question that we have here is why perverse sheaves? Why did we choose that to be our category of sheaves? And that has to do with sort of the last thing that we're looking for in our goal, which is to have the simple objects labeled by IC sheaves. I mean, well, spoiler alert, labeled by dominant co-weights. So maybe I'll just sort of write this as a fact, and hopefully we'll prove it at some point, but I'm not sure that we will. But perverse GO equivariant sheaves on GK mod GO is also a fact that Saad said are equivalent to perverse sheaves with respect to the orbit stratification on GK mod GO. So this is gonna sort of let us notice that strata are just in bijection with double cosets, which is, as we sort of noted at the beginning, in bijection with dominant co-weights. Maybe another fact is that all the strata are simply connected. So this is going to tell us that the simple objects are just given by sort of IC of some dominant co-weight of the stratum corresponds to some dominant co-weight. So, so this is pretty exciting. And again, it turns out, so maybe I'll write one last fact. Also, maybe I'll fix some more notation before I write that fact, which is that we're going to say Satake of G or Saad of G is going to be defined to be this category of perverse GO equivariant sheaves on GK mod GO. And then we have that sort of the Satake category and rep G check are both semi-simple. So at a level of, and again, this is something I hope to prove, but I'm not 100% sure we'll be able to get to. But at a level of simple objects, we do have, or at a level of abelian categories without any enrichment of a tensor structure, we do have Satake of G is isomorphic to rep G check is isomorphic to Z greater than or equal to 0 on positive co-weights. And this is just sort of something we can already see just based on what's been said so far. But what's hard is showing it's a tensor equivalence. So this sort of was very well known already before Merkovich and Volonin published their paper that we have an equivalence on abelian categories. But with hard, is you only have a tensor equivalence. So on the right, we're going to have a tensor product in rep G check. On the left, we're going to have some kind of a convolution very similar to what Saad described in his previous talk. But showing that those are going to be equivalent is going to be very hard. Or at least it's going to be the gist of why this proof sort of isn't trivial. Well, it's going to be harder, at least.
Hey, cool. Alberto?
Yeah.
Can I ask very quickly, can you just summarize that chain of logic that you just went over to get, like I guess from midway up the previous page down to Saad G, like just very quickly kind of.
Kenny, where do you want me to start, more or less?
I guess the geo acts on GK freely on the right.
Yeah, great. So the first idea there is we wanted to take, so our first try was to take like some kind of functions on double cosets, but that was pretty clearly going to fall flat. So we tried sheaves on double cosets. That wasn't a very meaningful statement. So we're going to try replacing sort of taking quotients with taking equivariant sheaves. So then GO acts on GK freely on the right. So that sort of tells us that when we take the first quotient, it doesn't really matter if we take equivariant sheaves or if we just take sheaves on the quotient. But GO very much does not act freely on GK mod GO. So sort of our model, maybe is a way to say it, for sheaves on those double cosets is going to be GO equivariant sheaves on GK mod GO. And if we take our category of sheaves to be perverse sheaves, that's actually going to get us the statement of geometric Satake, sort of written here at the bottom of this page. And then the last question I should have had before we moved on to like maybe more serious stuff is I asked like, why did we choose perverse sheaves as our category of sheaves? Because like it's sort of a common strategy going from like functions to sheaves when you want to make categorical statement, but why perverse sheaves specifically? And that's really more justified on this page. And the idea is that GO equivariant sheaves on the affine Grassmannian turn out to be the same as sheaves. Also, the affine Grassmannian is GK mod GO. Turn out to be the same as sheaves just with respect to the orbit stratification. And orbits turn out to be labeled by dominant co-weights. So we sort of said at the beginning that GK breaks into double cosets where there's sort of a dominant co-weight in the middle. And I mean, that's basically it. So then sort of we kind of went down and talked a bit about how at the level of just abelian categories, if we took these facts that I sort of wrote for granted, we would sort of already have an equivalence. We would already have basically a full proof. But what's going to be difficult is showing that's a tensor equivalence.
Okay.
Yeah.
So that correspondence between strata and co-weights, I guess that is the strata for this orbit stratification, not for the geo stratification.
Yeah. So it's the orbit.
Okay.
It's the I should write. It's the GO orbit stratification.
Okay.
Yeah. Yes. That's fair. I think that could have very much been unclear.
Okay.
But yeah, it's just the stratification of GK mod GO by GO.
Yeah.
Orbit. So the strata are just double cosets of GK or GO orbits of the affine Grassmannian.
Okay, cool.
Cool.
Thanks.
Sure. Yeah. Okay. So now that's sort of the end of motivation. And now we are going to begin to talk about the affine Grassmannian. So just define slash fixed notation, GR of G equals GK mod GO. Nothing too crazy. So maybe as a first sort of lemma slash example, so these affine Grassmannians do turn out to be, I mean, pretty involved objects, and we'll be finding a lot about them over the course of today and other days. But to start with a simple example, given a torus T, the affine Grassmannian of T is just co-weights, all of them. So why is this true? So an element of sort of the torus with coefficients in K is of the form, and let's just fix T is isomorphic to C star to the M, say, is going to look like sort of the sum from J equals Ki to infinity of Aij T to the J, and then sort of for one dem. So this actually, right here, this definition, when I write it out, it like looks messier than it is. It's just like all around series in each component. It's like C star to the M, the torus is C star to the M, and elements of the torus with values in K of TK just look like a Laurent series, just look like M Laurent series. That's it. But this is actually in the same sort of TO coset as just sort of taking the leading polynomial term without and getting rid of the coefficient. So it's just TKI from I1 to M. So why is this true? It's sort of evident-ish once you actually just look through what everything means. I think there's a lot of indices, which is frustrating. But if you were to just sort of take a quotient of these guys, then you would just get something in GO. You would get, as you're in degree 0, you just get the AIJs, the leading terms, and then you get like higher terms. But like the degrees on the top thing are straightly greater than or equal to the degrees on the bottom thing in each coordinate. So the quotient is going to be something in TO, and we get that this sort of element in the general form of TK is going to just be the same as an element. It's going to be in the same TO coset as an element in the very simple form. And elements in this form are exactly the ones that we recalled, just look like co-weights. So that's it. So the affine Grassmannian for a torus is a discrete set. It's very straightforward. So now let's look at sort of G reductive. Okay, so let's just define. So L lambda equals sort of T lambda times GO. So recall that those T lambda points are sort of co-weights taken as elements of TK, and then we're going to let GR lambda just be the GO orbit of these points. So it turns out we've sort of already said this, but we're going to sort of say it again in this notation, that the union of these GR lambda sets equals the whole affine Grassmannian, and furthermore, that GR lambda equals GR lambda tilde, if and only if they're in the same Weil group orbit. So in particular, we could just sort of say that we're only going to label them by dominant co-weights because there's exactly one in each Weil group orbit, and that's what we're going to do. So from now on, label, these are called Schubert cells. The G lambdas label Schubert cells by dominant co-weights. Okay, great. So theorem, each Schubert cell is simply connected of dimension equal to 2 rho times lambda. So I'm not going to prove the fact that they're simply connected, but I am actually going to prove the dimension count because most people don't, and it makes it feel like this rho appears somewhat magically. So this proof is maybe not super important to the overall flow, but I thought it was good to sort of explain where this rho comes from to a certain degree. But anyway, so let's go ahead. So GR lambda is the image. This is just sort of by its definition as a GO orbit of the map from GO to the affine Grassmannian, given by sending G to G times L lambda. And this map is surjective. Well, it's surjective onto, I'll just write the image is precisely that Schubert cell. So now the question is, what's the stabilizer? And then we'll have a good sense of what this variety looks like. And the stabilizer